Okay, so the topic of today's lecture is solution of nonlinear equations. Okay, now how this is different than the previous topic. The previous topic, when we have one nonlinear equation with one variable, and I want to find the roots for this. So we learn about the bisection method, we learn about interruption, etc. Now, when I have multiple of equations, so I have an n number of equations, and these n number of equations, they have an n number of variables, but these equations now are not linear equations. So it's not like what we did in the first part of the course when we solved linear equations. Now we are solving non-linear equations. Okay? And nonlinear equations, they do exist in many engineering systems. In electronics, we will have some examples that deals with nonlinear equations. In power engineering, we work a lot with nonlinear equations, and I'm quite sure in every discipline there are certain applications for nonlinear equations. Okay. So let's move on. So today what we will cover is the fixed point iteration or the Gauss-Seidel. The word fixed point and Gauss-Seidel, somehow they are, you can use them interchangeably. Fixed point is more common name than Gauss-Seidel, but Gauss-Seidel is also, you will see it in the literature. So either this or that, it means the same thing. So let's start. Okay, so now I have an n number of equations, okay, and these equations are non-linear equations. Give you an example, just a sec. For example, if I have this equation, x squared minus 2xy plus root of z equal to 0. Sorry. And x minus y squared, x squared over 2 plus root of y minus z equal to 0, and z squared minus 2xy equal to 15. Something like that. I could be any. So this is a set of nonlinear equations like this. And they have three they have an n variables, and we have an n number of equations. Here we have 1, 2, 3 variables, and we have 3 equations. Now, to use the fixed point as we did in Gauss-Seidel, or the fixed point when we did the finding the roots, we have to convert it in that format. So I have to have the x in one side and the rest in the other side. Then I have to have the y, and then we have to have the z. Now you could have many forms of this. Now, if we use this form or that form, does it matter? Yes, it does matter, and we will see that later on. Okay. So here I have to write this as x. This could be, for example, this equation. The first one could be like 2xy equal to x squared plus root z, then x is equal to x squared plus root z divided by 2y. So I put everything here to y, everything in terms x and the rest in the other side. So this is x1, and this would be like your g function, the g function. Okay. Then we come to the second equation, we put everything in one side and keep the y or the z, and then the same thing here as we did in finding the root or solving linear equations. It's the same approach. Once we put them in that format, then we start using our initial guess. So we have to have an initial guess because this is an iterative method. Now start with x1. So we have all the zeros. Okay, this is a good question here. It says here, can g of x include the variable we solved for? Yes, of course you can. Okay, so for example here, look to the first equation here. The first equation here, x1 equal to g1 and you have x1 also here. So you have x1 here and x1 there. But the difference between the two, this is known to me, and this is coming from what? From the initial guess. But this is my coming guess. This is the first iteration. So you could have x1 at both sides, or y, or whatever. Okay? So here we start with evaluating the first iteration of the first variable. So what we do, we use all the initial guess we have, so all of them at 0, meaning this is the initial guess. Then we move to the second, x2 of 1, and we do the same thing. Now here x1 will have two values. You have x1 0 and you have x1 1. This is the initial guess and this is the first iteration. What we use the most updated value, like what we did in the GS method, and we said that this is the difference between the Gauss-Seidel and the Jacobi method in the linear. It is exactly the same approach. Now, so in general, xi at 1, so up to I minus 1, we use the current iteration, and then the rest, which we don't compute yet, we use the previous iteration. So this is the general format. So for the ith variable at the kth iteration, up to I minus 1, we use the existing iteration. From I to the end, we use the previous iteration, because we don't have these values yet. And now what we do, we keep on doing this until we reach to accuracy level, until every single variable is matching the criteria that the error, percentage error, approximate relative error, whatever you want to call it, in the questions we might ask it for different ways. I might ask you until the error is 0.00001. So I'm talking about the relative. Not the relative, I'm talking about the actual error. If I divide by x of I k, then I'm looking for the relative error. If I multiply by 100, this is the percentage relative error. And it's always the difference between the existing iteration and the previous iteration. And the criteria has to be met for all variables, not just for one variable. Okay, so it is as simple as that. The only difference now between this and Gauss-Seidel, then now we are dealing with nonlinear equations. That's all. It's exactly the same thing. So let's start with an example here. So we have this equation that has been already set for us, meaning that we already put it in the format that x equal to g1 of xy, and y is equal to g2 of x of 1. So already set, we are already ready to start our iterations. Okay, and it says here that the relative approximate error is less than 0.1%. So this is my criteria. So I want to keep doing this until my error is less than 0.1%. And we'll start with x and y equal to 0, and this is in radian. Okay, so we'll start with x, first iteration equal to 0.7 sine of x, and this will be 0 iteration because I don't know the value of x yet. And here, for whoever asked the question, you can see x here and x there, both, plus 0.2 cosine, again 0 iteration because I don't have the value for y. So this becomes 0.7 sine of 0 plus 0.2 cosine of 0. So if you do that, this will go to 0 and this equal to 0.2. So this is my first guess for x1. Now let's do y1. This is equal to 0.7 cosine. Now I have x, I have two values of x. I have x of 0 and x of 1. Of course, I will use x of 1, the most updated value, minus 0.2 sine of y0. Why? Because I don't have a value for y yet. So this is equal to 0.7 cosine of 0.2 minus 0.2 sine of 0, and if you do this, this is equal to 0.68. 6.68047. Depends how many. Here I did not specify the number of significant digits. No, it depends on the question. You ask 3, 4, 5. You can limit that the number of significant digits. Okay, so we keep doing this until we reach to the error, which we said that we want the error to be 0.1%. Now when we look here, this is our first solution. Now we move on here and we keep our eyes on the error. So it starts with 3126. Now the error starts to drop, fluctuate a little bit, but eventually it is dropping until for both of them is less than 0.1%. You see here the y error is reaching the less than 0.1% criteria after the 12th iteration, but the x still at 0.3%. So I keep doing until the x is less than 0.1. Of course, now the y is way less than the 0.1%, and then this will be my stopping point. Okay, looks very straightforward, very nice. But as you know, our life as engineers is not always straightforward, not always free of problems. We are engineers, and meaning that we deal always with problems. Never ever that easy. Let's give an example here. So I want to solve again this nonlinear equation, and this nonlinear equation has two variables, which is the x and the y, but they are not given to us in the final format. So I have to adjust. So let's start with the first equation. So this is x squared plus xy equal to 10. Okay, there are multiple ways of doing this. One way is to do the following. Your xy is equal to 10 minus x squared. So your x is equal to 10 minus x squared divided by y. So this is my first equation. Before I move forward, there's a question here. Let me answer it. If y reached the required error range first, is it okay to stop iteration on y and only perform iteration on x with the value of y calculated in very last iteration? This is a very good question, but that's of course not the case, because for your x to if you are not changing the value of y, then you are not updating the answer of x. So you have to keep on changing the value of y. Otherwise, your x will stay as it is. If you are using the same value of y, eventually you will get the same value of x. So you will not move any forward. So this is why you have to keep on doing the y and the x and keep on doing the iteration. I hopefully this is clarified. Now another question, can I write this in a different way? Yes, you can. You can have this as 10 minus xy under the square root. This is another way. Yes, you can do that as well. Okay, so let's now see the second equation, which is 3xy. I can even here make it in terms of y, and the second one is for x. No one says that this has to be x and this has to be y. We could reverse it. So it's up to you. But now we'll see the fun part in a few minutes. Plus y equal to 57. Okay, again, I can isolate this either for y or for y squared. So I will keep it simple and make it for the y. So y is equal to 57 minus 3xy squared. Excellent. So I have the two equations now. Now I will start my initial guess. So this is your x, and this is your y. Okay, so now I will start. This is, let's say, the 0 iteration for x, and this is the 0 iteration of y. So let's start with x at the first iteration. Okay, so this will be equal to 10 minus x squared. So this will be x at 0 iteration squared divided by y 0 iteration. So this is the first thing I'm calculating. So everything will be 0 iteration. So this becomes 10 minus 1.5 divided by 3.5, and this is equal to 2.2143, something like that. Now let me do y at 1 is equal to 57 minus 3x1, most updated value, y 0 square, and this is, if you do the calculations, equal to minus 24.375. And we keep doing this, and if we do that, okay, let me just answer all the questions I have here before we move forward. 10 minus 1.5 squared. Yes, you're right. Yes, this is squared. Yes, you're right. Yeah, this is squared. Yes, you're right. Okay, so if you do that, okay, so this is the values that I have. Okay, now this is the full answer. Start here. So this is my initial guess. Now, if you look to the x, going here, it's going to a very, 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 very small number. Going to the y, it's going to a very, 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 very large number. So it's very obvious for me that this simple equation does not converge. Okay, so we need to find criteria. Back to what we did before. What is the criteria? How I can tell if my system or of my system of equations will converge or not? Here we come to the correct criteria for conversion, which is the following. Now, for two variables, the partial derivative of g1, the first function with respect to x, plus the partial derivative of g1 with respect to y is less than 1. Also, the partial, all of course, absolute values, and the same thing for g2 is less than 1. If this condition satisfies, then we will have a convergence guaranteed. Let me check this. Let me see here. This is my equation that I have before. So this is my g1. Basically, this is my g1, and this is my g2. Okay, so let me take the partial derivative of g1 with respect to x. Now I will evaluate this at 0 plus the partial derivative, because this is our initial guess. So the summation of the partial derivatives with respect to the variables is absolute value. It should be less than 1 at the initial guess, because it could be at another guess, it could violate the conditions. Okay, so this is the criteria. So this is equal to, take the partial derivative of this with respect to x. So this is goes to 0, so it becomes 0.7 cosine, and this would be a 0 because this is my initial guess. Plus, come on. Okay. Plus the partial derivative of g1 with respect to y. So with respect to y, this goes to this becomes equal to 0.7 sine of x. Take the derivative with respect to y is equal to 0. Take this one, the second term with respect to y. So this becomes minus 0.2 sine of 0. And this is equal to 0.7 plus 0, which is 0.7 and which is less than 1. Now let's do the second one, which is g2. So we'll take the partial derivative of g2 with respect to x plus the partial derivative of g2 with respect to y is equal to the same thing here. Take the partial derivative, and you will find this is equal to 0.2, which is also less than 1. So both conditions have been satisfied. So this is why this is no, it has to be less than 1, not equal to. It has to be less than. That's not equal. It has to be less than 1. Another question here. So to do this check, do we plug in the initial values? Yes. Because this is our initial guess of the question is, so to do this check, do we plug in the initial values of x and y? Yes. Why initial values? Because this is the initial guess of our solution. So we start with this. Okay. If we have a different, because choosing the initial guess, and now with this criteria, you can go and try that. You try something that is might vary, but you'll see that here. I don't think that there will be in any way that you can come up with an initial guess that make this not less than 1 in all cases. But if you change the variables here, instead of 1.7, make it this 1.5 or something, then your system will not converging, and you can prove that. So we can make an initial guess in other functions that could cause them to diverge. Yes, in certain functions, yes, it might converge or diverge. In some, no. Regardless, because here the function is very obvious. You can't get more than 1 because one of them will be 1, one of them will be 0. And since the factor here is 0.7, 0.2, so it will always converge. Now let's see the other question, which is this one. Okay, so this is my now G1, and this is my G2. So take the partial derivative of G1 with respect to x plus the partial derivative of G1 with respect to y. Okay, so this becomes, take the partial derivative of this with respect to x, so it becomes 10 minus 2x divided by y, plus take the partial derivative with respect to y, so this becomes y squared minus 10 minus 2 minus x squared. Okay, now if you substitute here, you will find this is equal to 2.632, which is obviously greater than 1. And now, if one of them violates the condition, you don't need to one of them is sufficient, because you have to have all of them satisfy the condition. But if you do the other one as well, if this is G2, if you take G2 with respect to x plus G2 with respect to y, if you do the same thing, you will find this is equal to 45.75, which is also more than. So this is why this failed to converge. Let me see your question. Okay. Okay, there's one question here. Let me read it loudly. So for a system of n nonlinear equation, is the condition adjusted so that the sum of the absolute value of the partial derivative with respect to each one is less than 1? Yes. That's the criteria. When you make your equations, you have to make sure that your equations are organized in such a way that the summation of the absolute value of the partial derivative is less than 1. And this doesn't sound straightforward. And this is why we need to have a better technique. And to show this to you, I have an interesting proposal for you, which is called bonus challenge. This is 1%. Okay. Now, this is the set of equations that we had. Okay. So, x squared plus xy equal to 10, 3xy squared plus y equal to 57. The question is, I want you to come with a correct set of equations that will lead to convergence. Okay? And you can use MATLAB to show this, because you notice that you need a lot of iterations to show, because the conversion will be very, very, very slow. So you can use MATLAB. That's not the issue here. I already have a folder for the quiz open, and this quiz is open until next class. Okay, let's see who can come up. You have to prove it to me, not just give me the function. You have to show that if you do this, and as I said, maybe a small M file, you can include it in your solution that shows the convergence. Very straightforward, just two equations. You start with the initial guess and then keep on doing this, and then you will see that the answer is it converging or not converging. Okay. Is the bonus for the first person to get it? Okay. Now this one, it is the bonus for if you get different functions. Anyone come up with a different function, you will get the bonus, not just the fastest one. This is why I gave here long time for the quiz, so everyone come up. But if you get this formula, there could be multiple solutions for this problem, not just one solution. Okay, so if you get this solution, okay, that's okay. If someone come up with another solution, then definitely he or she will get another the bonus question, etc. Okay, so have fun. Okay, so this is the last thing I want to add, or I want to conclude my lecture with, which is a practical applications. I always like this part of the course. I always like to have some practical touch, so that you don't feel that the course is just some numerical method that doesn't have any applications in our life. And as I mentioned, the diode, maybe you've already started it, or you will start soon. Working with it, and you will work with the nonlinear equations. So now you are ahead of the game. You know what is a diode and what is its equation, what is the nonlinear equation, what is the linear equations, what is the approximation about the diode. Okay, so that's also foster intercourse relationships. Okay, so here I have two diodes, and I will have ID1, ID2, and I3. So I'd like to solve for ID1 and ID2, so I need two equations. I have to have two equations to be able to do that. Just to remind you that the voltage across the diode, VD, is equal to a constant called VT, which is 25 millivolt for the silicon type of diode, okay, times ln the current I, which is here in this case is the ID, the current goes through there, divided by another constant, we call it I of S. And I of S is 10 to minus 12 amps, so it is a constant. So this is the nonlinear equation that actually relates the voltage of the diode with the current that goes through the diode. Okay, so since we have two diodes, I will have two nonlinear equations. So if I take a KVL, okay, so I will take KVL for this loop. Okay, so I will call this is VD1, and this is obviously VD2. Take a KVL, so you'll have, and this the current is ID1. So so the PS is 10 volts. So 10 volts equal to 1000 ID1 plus VD1 plus VD2 equal to 0. Just a KVL here. Okay, I don't want the equations to be in terms of VD1 or VD2, but instead in terms of current. So this will be equal to 1000. This is 10, of course, it's a constant. 1000 ID1 plus VD1, which is VT constant, ln ID1 divided by IS, another constant, plus same thing. This is KVL. I'm applying KVL. No, there's no zero. Sorry, that's not zero. plus Vt ln ID2 divided by I of S. Okay, so I have this is ID1. So I have one nonlinear equation with two unknowns, ID1 and ID2. So I need to come up with the second equation, the second nonlinear equation. So I will apply KCL. So this is coming from KVL. From a KCL, I have ID1 equal to ID2 plus I3. So this is the second equation. But now I'm introducing another unknown, which is I3. I don't want to have I3. I want to have, again, in terms of ID1 and ID2. But what is I3? I3 is nothing but VD2 divided by R, which is in this case 1000. And we know that VD2 is equal to what? We know this is equal to VT to become over 1000 ln ID2 divided by I. So if I come and substitute this value here, I have my second equation in terms of ID1 and ID2. Let me just go through this. So this is my ID1 now. This is ID1. Now what I do here, this is the equation I just found. Now I need to write this in terms of ID1. As we said, we have to have everything in terms of ID1 equal, ID2 equal. Okay, so these are to my variables. So what I did, I take all this, moved it to the other side here, okay, and then divide by 1000 to make this is ID1. So this is why we have here 10 over 1000, 0.01 minus 0.0258 times 10 to minus 3 and minus the other term. So this is my first equation in the right format. All of this will be my G of ID1 and ID2 and equal G1. This is my second equation I just showed you from KCL. And now ID1 is equal to ID2 plus this. This is your I3. Now I don't want this to be in terms of ID1 because I already have an equation in terms of ID1. So I need this to become in terms of ID2. So I will just move this part here. So I have here ID2. Now this is my G2 in terms of ID1 and ID2. So I have the two equations now ready. So what I need to do, I need to start with an initial guess. Now why I started with this? This is by, again, in dealing with practical problems, understanding the physics of the problem is very, very important. So I know that having a voltage here is as 10 volt, having a resistance here which is 1 kilo ohm. I know another one is 1 kilo ohm, so I know that the current will be in the milliamp range. I know that for a fact. Not 1 milliamp, maybe a bit more than that, but I don't care because the system will converge. Okay, so I start with this 1 milliamp. Now, if I want to find an approximate value, what is ID1 and ID2? We said that we can have this as a short circuit. If this is a short circuit or a 0.7, either this or that will give you. But I'm not using the bisection method here, so I don't need to have a limit. I need just to have one value. So if I have this as a 0 short circuit, another short circuit here. Okay, so this will be a short circuit, this will be a short circuit. So the current here, ID1 and ID2 will be the same because this will be cancelled. And the current will be the 10 volt divided by the 1 kilo, so it will give you 10 milliamps. So a better initial guess, it could be 10 milliamps, but I just started with 1 milliamp. Okay, so, and you see here that the answer jumped from 1 milliamps for both ID1 and ID2 to 8.931 milliamps, and for ID2, and here I can see I'm using the most updated value for ID1, and here it is the initial guess for ID2. So they jumped, and this is what I'm expecting, because the answer I'm expecting is close to 10 milliamps. Now, it will not be 10 milliamps because there's a voltage drop here. It will be less than 10 milliamps. So the answer looks for me very, very close. And this is something, again, I'd like to stress. When you deal with the practical problems, you need to understand the physics of the problem, and you should have an idea where is your answer. Okay, so that it's not just you are engineer. We are not just programmers that we just take equations, we program them, and we have no clue if this makes sense or doesn't make sense. It is always, it's very important that you understand the physics of your problem. Hence, you understand where should be your answer. Okay. Now, if you do that, just a couple of iterations, we have reached to a very good accuracy. So the problem converged around 8.820 and 8.31. I just have showed to you that if I assume the diodes are short circuit, which is one extreme, both ID1 equal to ID2 and equal to 10 milliamps. This is one extreme. If we assume that this is a 0.7 voltage drop, which is the other extreme, and your answer should be in between, you will find that the answer is somehow in one of them 7.9 and in other one it's 8.6. So somehow your answer is around these